Welcome to this demo about the ArrayList defined as list class in the Java Collections framework. In this demo I'll examine how an ArrayList behaves when appending elements to the end. There are two methods that I'll examine as defined in Java 11. A one-parameter add method to which I can pass an object. That method appends the specified element to the end of this list. And a one-parameter addAll method to which I can pass a collection of objects. And this method appends all of the elements in the specified collection to the end of this list. And this is my sample code. First note, Collections framework classes are defined in the Java util package. In the main method I start by creating an ArrayList object designed to hold integer values. The Collections framework is a generic framework, so I specify integer, the wrapper type class, by using the generic syntax. Note as well, since ArrayList implements the list interface, I define my variable of type list. A good coding practice: specify your local variable type as high as possible in the hierarchy. This will make your code more reusable. After the creation, I'll add a first element, an integer constant, with a value of 210. ArrayList is known as a dynamic resizable array, and the name is very well chosen, as you'll find out when I analyze this statement. Then I'll add more elements by invoking the addAll method, to which I can pass a collection of constants using the arrays as list notation. And I repeat executing similar statements a couple of more times. I use a list utility helper class to print the items on the screen, and executing the whole program will provide following output. So just all the elements that are added, since I only print once here. But in my demo I'll show outputs after several statements. Now, as mentioned in the comments, sometimes adding an element causes a resize, but not always. So what triggers the resize, and what does a resize mean in the first place? Let's find out in the memory layout. For those of you new to my channel, this is a layout that I explain in my other playlists, Java Under the Hood, Stack and Heap Memory Fundamentals. So if you're not familiar with all that is written here, I advise you to watch first some other videos of that playlist before watching this video. Okay. Let's begin with the creation of the ArrayList object. So the local variable nrs is allocated in the stack frame. Now, in order to understand the instantiation, let's first have a look at the definition of ArrayList as defined in the GDK. And so I'm using Java 11. In order not to create too much overhead in my demos, I only display the relevant information of the class. First note, two important instance data members: element data and size. Element data represents a reference variable that refers to an array containing the actual data added to an array list. The elements are of type objects, meaning you can add an object of any type except primitive type variables. Second instance data member is size. It represents the number of elements the array list contains. In the constructor, we note that initially element data will refer to a default capacity empty element data. This represents a reference to an empty array in a method area, since declared static. Don't worry too much about this empty array, since it will not be used for long, as you'll see. After executing these statements, we have the following in memory. So the local variable nrs refers to an object at fictional address 1000 containing a size of 0 and element data pointing to initially the empty array. Have a look at my fundamentals video about static if you don't know why static leads to something being allocated in the method area. Okay, our ArrayList object is created. Let's now add an element, an integer constant 210. Now, since data structures in the Collections framework, as mentioned before, such as ArrayList and linked list, only allow objects to be stored and not variables of a primitive type, The first thing that happens before the actual add method is invoked is that its sole parameter must receive an object. So out of the 210 parameter, an integer wrapper object will be created. This is known as boxing and carried out in the value of method of the integer class, of which the GDK code is displayed here. What happens in memory when invoking this method? Well, let's set up the stack frame. So this is a static method. So my current stack frame becomes the value of method. There's no this pointer because it's a static method. So my first variable in the local variable array is this parameter I, which represents the constant 210 we want to add. In the value of methods, then a test is carried out to see if the value of the parameter, our number 210, is greater than or equal to integer cache.low, which represents the value of -128, and less than or equal to the high limit, which is +127. This is an integer cache from which we can retrieve elements more quickly. But this is not our case, so instead of retrieving an already made object in the integer cache, an object of wrapper type integer is created on the heap. And I add the object at fictional address 3010. Specifying the return value, so assigning the value to the return value of the methods, then leaving the methods, clearing the stack frame, but the Java runtime holds on to the wrapper object since we're in the process of invoking the add method, to which we pass now the reference to this object as argument. So method add of ArrayList is invoked. And again, GDK code. The reference to the wrapper object is passed as arguments. And let's set up the stack frame for this method. So now we have an instance method call. This is not a static call. So the first variable in the local variables array is the this pointer, and the value of our nrs variable, which points to our ArrayList object. The second variable is the e, which is a reference to the wrapper object that has just been created. Then within the same ArrayList class, a private add method is invoked, passing the reference e, element data, and size. Now these two are prefixed by this dot notation. Since not declared as variables in this method, it implies that they are member variables of the current object. So if we go to this, we dereference dot, and then we see the current value of size 0 and element data and the address of 1100 pointing to the empty array. So these three values will be passed to a new add method, e, element data, and s. So let's set up the stack frame of this method. So this is an instance method call. So first is the this pointer referring to the ArrayList object. Second is the e 3010, element data referring to our empty array, and the s that got a value from size, which is 0. Now about this notation, these are just code snippets that I've put together. Of course, in Java, nested methods are not allowed, so you'll not find this exact same code in your Java libraries. But for demo purposes, I find it easier sometimes to use this notation to display the sequence of method invocations. Okay, now this method first examines the length of the array. Element data.length, which is 0 because we refer to an empty array. And if that value equals s0, then the array will have to grow. Now, since the length of an array in Java cannot be changed, growing an array means that an entirely new array will have to be created. And this is done in the grow method, of which I don't display the GDK code. I'll just show you what happens in the heap. So what it does is it creates an array with a default capacity of 10 elements here at fictional address 2000. Since my slide is not wide enough to represent all the elements, I only display the first and last of them. Know that for the items in the middle, represented by 3 dots, similar actions take place. Since ArrayList internally manages an array of objects, I should say manages an array of references to objects, Initially, each reference element holds an address of null. I have a video about this as well in the fundamentals playlist, array of objects. Now, still within the grow method, once the array is created, element data member, will now refer to this new array. And after that, the return value of grow is assigned to the element data local variable, or parameter, I should say. And so, element data parameter will refer to that array as well. Then the new element referred to by E is added to the internal array at the first position. E is our 210, wrapper object S is 0, so in this area at position 0 we add our first element. Finally, the size is set to 1, S plus 1, so 0 plus 1 is 1, and that is assigned to this.size. Voila! We leave the add methods. Okay, now we're back at the previous add method. The return value receives value of true, but I don't do anything with it in the main methods, so it's not assigned to a local variable in the main method, although I could have done that, but I didn't do it here. We're back at the stack frame, and our first element has been set up. If we were to print out the content of the array, we could get a sample output that looks like this. Next, let's fill the entire array in one go using the ArrayList notation. I'm not going to show the GDK code for the addAll method, just the animations in the heap. addAll will first, as we had for the 210 constant, we created a wrapper type object. This will be the case as well for all these constants. So for first, all wrapper type integer objects will be created, and then each element will refer to one of these wrapper objects. So this is the effect of the addAll method receiving a collection of constants, and the size is set accordingly now to 10. If we were to print out the output now, we would get 10 elements. What happens when I add another integer constant, say 310? Now, before doing that, I'll clear up the slide a little bit because I'll need more space on the heap. Since the array in the method area is not used anymore, I'll remove the method area altogether from the slide and extend the heap a little bit. Okay, back to adding to 310. We first create a wrapper integer object holding the value of 310 at this fictional address. Now, since the internal array is full, it'll have to grow again. Since an existing array cannot be extended, as already said, an entirely new array will be created once more. This time with a capacity of 15 elements. So index 0 to 14, 15 elements, and element data will refer to that new array. And after that, and this is important to note, before we add the new element, we first copy all the existing elements of the previous array into the new array. And then the new element, the integer object 310, is added after the last element. And the size is incremented to 11. Now let's pause here for a while and analyze this behavior, which is typical for ArrayList. Adding a new element to an array containing 1 million elements will take longer when a resize takes place than when adding a new element if the ArrayList contains just 10 elements. We can express the performance of the ArrayList add method by using big O notation. Big O defines a relationship between the time an operation takes to complete and its input size. The add method is interesting with regard to big O in a sense that two relationships can be noticed. First, when an enlargement does not take place during an add operation, the time the method takes to complete is independent of the amount of elements stored in the internal array of ArrayList. In other words, that time is always the same. It is constant. We express it then as O1. Second behavior, when an enlargement does take place during an add operation, the time the method takes to complete is dependent of the amount of elements stored in the internal array. So the more elements an ArrayList contains, the longer the method will take to complete. We note a linear relationship and express it then as O(n). N represents the amount of elements stored in the array. Each time you enlarge, you take longer than the last enlarge, but you've also waited longer than before doing it. The cost of each enlargement can thus be spread out among the insertions, and we call it amortized O1. What does it mean? It happens more often that an element is added without an enlargement taking place than when enlargement takes place. So there are many more O1s than ON. So amortized O1 means it's not strictly O1, it's not strictly ON, but it's closer to O1 than ON. Okay? Now, the previous array, since not referred to by any reference variable anymore, will eventually be cleared by the garbage collector of the Java virtual machine. And I simulate this now, so in order to clear up the slide a little bit. An output of the ArrayList now yields 11 elements. Before continuing, now personally I find the name of size property of ArrayList quite unfortunate, because size to me invokes the idea of size or length of an array, which in our example is now 15. But note that instead it means the amount of elements that currently are stored, which is 11. Don't let the name confuse you. Okay. We still have 4 places left in our array. If I were to add one more element using the add operation again at this stage, resizing would not be necessary, and thus that add operation would execute quickly O1. So as long as a resize is not necessary, an add operation is much quicker than when the operation triggers a resize, even if I would fill up the free space with addAll right now. There are 4 places left. I add 4 elements. It means no resize. So I add 4 more elements. So 15 elements displayed in the outputs. The last thing I want to bring to your attention is resizing of the internal array. Our array is currently full. So the length of the internal array, element data.length, is equal to the size property of ArrayList. Remember, size represents the amount of elements actually added to the array. And so what would happen if we were to add another integer, say 360, using the add method? Well, another grow or resize of the array will take place, and this time to 22. But why 22? And what if we would add a list of a lot of elements using the addAll methods? Then there's a resize to, well, which formula is used to calculate the new size then? Well, whenever a grow is invoked, method new capacity is executed along its path, which contains the following code. So this is still within the ArrayList class. I have removed some additional checks that take place in this method. So the main idea of this implementation is what is displayed here. Now, parameter min capacity and new capacity are important here. If we were to add one more integer, say 360, that would mean that this method will be invoked with parameter min capacity equals to the size plus 1. So the current size 15 plus 1 is 16. The new capacity is calculated as being all capacity, element data.length, which is currently 15, plus all capacity and 1 bit shift to the right. So it means new capacity 15 plus 1 bit shift to the right basically comes down to a division by 2. Strictly speaking, 15 contains 4 1 bits. 1 bit shift to the right means 1 bit falls off, so to speak, so remaining are 3 1 bits, and that is a value of 7. So 15 plus 7 is 22. What is done with these two values? Where they are compared in the if statement, basically what it says is if the minimum capacity that we need is less than what I can give you, then we have enough, and then we return the new capacity value of 22. In the case of if we would add a list of numbers, let's say 27 numbers, Then again, using the same formulas, min capacity would then be invoked using size plus 27. So current size 15 plus 27 is 42. The new capacity would be 15 plus, well, it's the same formula, so value of 22. The result in the if statement will be negative, so this if becomes true, and then we will return the minimum capacity. Because minimum capacity means the amount we really need, but you can provide only 22. That's not enough, so I'm going to need 42, and then we return min capacity of 42. To resume, add and addAll. So those two methods add elements to the end of the array list. Both methods will, whenever more space is needed, create a new array and copy elements from the old to the new array, which is on behavior. Just adding an element without a resize is O1, which takes place more often than a resize. And that makes these add methods to be amortized O1. Okay, that's it for this demo. I hope you have a better understanding about the add methods of ArrayList. Thank you for watching and for liking my video or subscribing to my channel. Bye bye.